Okay, so today we're first going to talk a little bit about the chapter 2 quiz. And this quiz is better than the first one, the chapter 1 quiz. And I can see the performance is improved a lot, actually. So, so let's see, here's the problem. So, okay, so I can see that there's, so I will mainly going to say something about the two problems. Number 1 and number 5b. Okay, besides these two, the other problem is it's okay. There's not big problems. Okay. Now, first one is a variation of the exercise problems. Okay, so I'm going to tell you, explain to you the important detail here. So for this problem, so the only difference is that n is replaced by square root n. Okay, this makes some change of detail in the proof. Okay, so we begin in the regular way. You observe that 1 plus square root n to the power of 1 over n is greater or equal than 1. Okay, obviously, so therefore I can set this equals to 1 plus bn. Okay, so bn is defined through this expression minus 1, which is greater or equal than 0, obviously. Okay. Now, the thing is, I have to turn the estimate to the bn. So this is what we're going to do. I take n's power on both sides. Okay, so you get 1 plus bn to the x power. So using expansion, this is greater than 1 plus nb. Now, this is the key details. Okay, we know that expansion is like this. Okay, 1 plus an equals 1 plus na, then plus other terms. So as you have terms going higher, you can see there's more involved, more power of n. So what kind of term you should involve? And in the homework problem, you need to involve the third term, the n times n minus 1. So then basically you have n squared term there. The reason we want the n squared term is because that previously you have 1 plus 2n on the left side. So you have n on the left side. So that's why you're including 1 plus the third term. Now this time is different. On the left side, there's only square root n. And square root n can be handled by the nth term, that means the second term. So that's why I only need the first term plus the second term. So that's how I get a estimate from below, which is greater than or equal to 1 plus n times bn. That will be enough. You don't have to include the high order term. Now, if you include high order term, that's fine. But however, you just complicate the detail of the proof. Now, including 1 is because on the left side, there's 1 involved. So including 1 enables us to cancel that 1. Okay, so therefore you get a nice estimate for bn. Bn is less than, cancel 1 divided by n, you get the 1 over square root n. That's sufficient because when n goes to infinity, then 1 over square root n will goes to 0. So that will be enough. So the problem is reduced to show that 1 over square root n less than epsilon. Okay, so therefore now you can start with the main paragraph of proof. So for any epsilon greater than 0, you can choose k greater than 1 over epsilon squared. Now the square corresponds to the square root. Okay, you will see in a moment. So this means that when n greater than k, the n will be greater than 1 over epsilon squared. So this will give us 1 over square root n is less than epsilon. Okay, so this will give us, by the previous argument, you can see that bn is less than epsilon. That will be sufficient because the final inequality says like this expression minus 1 is exactly equal to bn less than epsilon. So that's the way how to prove it. So that's why you can see a tiny bit change of detail requires us to think carefully on the middle of the proof, some of detail. You need to adjust something. Okay, you cannot just copy the previous proof, otherwise you are just complicated the argument. So this is I can see a number of students can handle this correctly. So, okay. So another problem I want to talk about is the last one. So that's 5B. 5B is very similar to the whole, to one of the example in the notes. In the notes, you have power to the 2, right? Now here is factorial, 2 factorial, 3 factorial. Well, there's no much big difference, okay? I'll show you how I can handle this. So our goal is to show that the Xn is a Cauchy sequence. So for every epsilon greater than 0, so you go with the definition. Now here, there's a technical assumption. You want 2k minus 1 greater than 1 over epsilon. You want this happens in order to go to the final inequality. So you will see why we made this assumption, why we choose k like this in a moment, okay? So let's say that you have two indexes, n and m, both greater than k. So this means that you are going to have this less than epsilon, okay? Now you look at using the Cauchy criteria, okay? You can estimate the difference, xn minus xm. And what we want is to show that this guy is less than something, right? Less than epsilon. That will be sufficient. Now it's come to a number of terms on the right side, starting from 1 over n plus 1 factorial, all the way to 1 over n factorial. Now, how do you estimate this? Okay, so you can actually factorize the first term out, but that's the one way to go, okay? But still, you need to estimate the summations. Now, in the previous case, you have a power term, the 1 over 2, 1/2 to the nth power. The power term can be estimated using summation formula, but there's no such a summation formula for the factorial term. Now, how we can handle this? And actually, there is a way, because you know that when you estimate this, all you need to prove is that this difference is less than epsilon. We don't need to prove a very accurate summation of these finite number of terms, okay? So therefore, I can first estimate this. Now you can see that there's a factorial involved. So each term, like the first term, 1 over n plus 1 factorial. Now what can you say this fraction? So in the denominator, you can see that there's except the first term 1, you can see start from 2 times 3 times 4 up to n plus 1. So you have m integer, the product of m integers. And all these integers are greater or equal than 2. Okay, think about this way. So you can see that the first term simply can be estimated using the power term. It's less than 1 over 2m. Okay, and the next term have one more factor involved, n plus 2. So they are going to be n plus 1, the product of n plus 1 integers. All these integers are greater or equal than 2. So therefore, the second term can be handled by 1 over 2n plus 1, and all the way to the n factorial. Okay, so therefore you can see, then it's reduced to power term. Okay, it's reduced to power term, and you can see that eventually it's less than epsilon. I mean, it's going back to the example in the notes. You can handle this. Okay, so that's how we can handle the 5B. Okay, so that's the things I want to review with you about this homework, about this test. Any questions? Okay, no question. Then I can start with the new material today. Okay. Okay, now let's continue. And we are already in chapter 3. And chapter 3 is talk about the topology in the Euclidean space. It's not a one-dimensional topology, it's a multi-dimensional topology. It can be considered as an abstract n-dimensional Euclidean space. Okay, so this is a very important chapters in which we are going to introduce some of the very important notions. But however, now we are in the beginning of April. We basically have a month or so to finish everything. So therefore, we have to be a little bit hurried. Okay, so I'm going to teach those material selectively. Okay, I'm going to only just talk about the important stuff. Okay. Now, last time we talked about, so we're talking to the first thing we'll talk about open and the closed set. Okay. Now let's talk about, so last time we talked about open set. So what I mean by open set, this means that every point inside the set, okay, also contains a ball centered at this point. So you can see that in the picture, you can see two point inside, and you have two balls. I mean, as long as the radius is small enough, so this ball will be completely inside G. So that's a requirement for G to be an open set. Okay, so open set cannot carry any boundary point. So you can see that there's a point on the boundary. Obviously, if you take any neighborhood, no matter how small the radius is, this neighborhood, this ball cannot be completely inside G. No way. So as an open set cannot carry any boundary point. So a typical example is like an open interval or open ball. So those are open set. Okay. And then we talk about the open set properties. So these are a fundamental property of open set. Now, when you talk about this property, we have to make some special arrangement. We define. Now, when we talk about empty set that means a set without any elements. So this set is considered an open set. Okay, it's defined to be open set. And then the whole space is an open set. It's followed from definition. Okay, so the first property is V is an open set. This is a definition. And RP is an open set. This is obvious by the definition. Now, part B is the intersection of any finite collection of open set is open. I mean, we talk about there are several open sets. You make a intersection of these open set. Okay, then the resulting set, much smaller, should also be open as long as the number of open sets involved is finite. Now, there are some situations that you have infinite open set, the intersection will still be open. That's possible. But however, without finiteness restriction, and this is it's not going to be a general result. Okay, so this means that if it is possible, just last time we see an example in which there's infinite number of open set, the intersection give you actually a close. It's a non-open set. Okay, so that's why for B, the finiteness restriction is necessary. Now part C is about union. Then there's no restriction, no matter how many open sets you have put together, and the union is always be open. Okay, so this is something we have done already last time. Okay, now today we are going to talk about closed set. And last time we actually defined the closed set. Now what I mean by a set is closed? It's closed set. Now roughly speaking, it means that the complement RP minus F is open. So when you look at a set is closed or not, you look at the outside. If the outside the complement is open, then you can see the original set is closed. So that's a official definition for closed set. Now, one thing you can see clearly that the closed set always contains the boundary. Why? Because you look at outside. Look at outside, the complements sharing the same boundary as the set itself. Okay, they're sharing the same boundary. Outside and inside, they're sharing the same boundary, right? Okay. Now, if the outside is open, so outside is not going to carry any boundary point. So all the boundary point will belongs to the set itself, the F set itself. So that's why if a set is a closed set, you can see, well, here we haven't really defined what it means by the boundary yet, but from picture you can roughly see that it must contain all the boundary point near the boundary. Okay, so example is a closed interval A to B and a closed ball. Okay, now here we are going to talk about a similar theorem about a closed set. It's called closed set properties. So it's the same thing, similar. Here I have some typo I can see already. Now the part A is saying that both empty set and the entire space are closed, not open. So I should make a correction here. So previously we see that the empty set and the whole space are open. Now I can see that the empty set and the whole space are closed. Now why is the case? This is because that the empty set and the whole space, they are mutually complement to each other. So for instance, the complement of empty set is the whole space. I know the whole space open, so therefore the empty set has to be closed. Okay, so for the empty set, this set has to be both open and both closed. For the same reason, the whole space is open set and also a closed set because its complements is an empty set which is closed. So part A is trivial properties. Okay. Now part B is about intersection. Okay, intersection, and actually in this case you can see this closed set property is opposite to the open set property. Now remember in the open set property it says that intersection of finite collection of open set is open. Now you can see here the part B of closed set property, the finiteness restriction is removed. The finiteness restriction is removed. I mean the intersection of any collection of closed set is closed. No restriction of there's a finite collection. So we'll see why. And part C is talk about union. And then you can see for the union is opposite to the open set property. This time you can see there is a finiteness restriction. That means only a finite collection of closed set is closed. Now suppose you have a infinite number closed set, then the union may not be closed. Okay, maybe open or something else. All right, so be careful. Okay, so now we are at a point trying to prove this property. Okay, so as we can see previously, and the part A is obvious from definition. So let's see how do we prove the part B. Part B is about the intersection, right? So now in this case, there's no restriction on the finiteness. So therefore, we can consider F alpha. F alpha is a family of closed set, finite collection or infinite collection, even non-countable collection. So we haven't talked about countability assumption yet. Okay. So sometimes index I use alpha or beta index. This means that the family is a non-countable, can be non-countable collection. Okay, so that's the situation. Now, when you want to prove the closed set property, we want to make a connection to the open set. Okay. Now the connection is the complement of open set is closed. So therefore, the complements of closed set is open. Okay, they're mutually complement to each other. So that's a follow definition. But however, we need to know a little bit further than that. Okay, now remember in the set theory, we have a result like this. So take an intersection of a family of F alpha. I mean, what is the complement of the intersection? And then the set theory tells us that the complement of the intersection equals the union of the complement. Now, this is the key set identity I'm going to use to produce the closed set properties. Okay, so this is done. This is proven in a more elementary class. So I'm not going to mention this property or showing you this property anymore. All right. Okay. Now we begin with F alpha is closed. Okay. So by the definition, you can see RP minus alpha, the complement is open by definition, okay? And therefore, the right side will become a union of collection of open set. Now, what happened for the union of collection of open set? It will still be open, right? By the open set property. So the right side is an open set, okay, by the open set property. So therefore, this indicates the left side is also open. So the left side is open, and the left side is the complement of the intersection. So this is just saying that the intersection of the complement, the complement of the intersection is open. So therefore, the complement itself, the intersection itself is closed. Okay, so that's how we prove the part B using this identity. You can directly reduce the closed set property to the open set property through this identity, and also through the definition of closed set. Any questions? Okay, so let's see. So that's why the proof is complete. Now let's see the part C. It follows from the same, using the same identity, follow from the same idea. Now this time, let's say that F alpha is a finite collection of closed set. Okay, finite collection. So union intersection doesn't tell you whether it's a finite or infinite, but let's assume that it's finite. Okay, so therefore using the same similar identity. Now the similar identity saying that the complement of union equal to the intersection of the complements. Okay, that's the same identity. I mean similar identity to the first one. Okay, now we can argue in the same way. Now suppose, now since F alpha is closed, so therefore by definition you can see the complement is open. So therefore the right side, now you can see it's an intersection of a finite collection of open set. And by the open set property, we can see that this intersection, because it's an intersection of all open set, it has to be open. It has to be open. So therefore the left side is open. The left side is equal to the complement of union. So that this shows that union is closed. Okay, so this is, you can see the argument is based on this identity and using the definition. Okay, so this is the way we proved the closed set property. Okay, so that's a very simple properties. Okay, questions? Okay, no questions. So yeah, there's a. So the question is, if there is a set R and a closed set F, does this means that a point cannot be found within F for parentheses Rx? I not quite understand these questions. Is there anyone can explain that to me? Okay, we'll talk about it after the class. Okay, yeah. Okay, so let's continue. Okay. So next thing we want to do is we're still in the 3A. Okay, now we have to define something else. Now here we have defined two special sets. One is open set and one is closed set. So these sets are very special, but there are many other sets. They are neither open nor closed. Okay, how do we handle the other kind of set? So this is our next question. So here we are giving with a set A in RP. So actually in the picture, I draw this set. You can see this set is not open, not closed, because you can see the solid line indicate those points are inside A. and the broken line indicates that this portion is not in A. So you can see the boundary, and a part of boundary belongs to A, a part of boundary is not in A. So this, you can see this is not an open set and not a closed set. And there can be any other set which is much more complicated than this. So the main question is what we can say about a general set. The point belongs to a general set. Now, for a general set, we can distinguish three different kind of points, okay? So given a set, we can define three different kinds of points associated to the A. Okay, we're going to define it one by one. So the first kind of point is called interior point. Now, what I mean by interior point? So for instance, a point is inside A. Now, what I mean by this is an interior point. Interior point means that there is a ball, small ball surrounding this point. The whole ball is inside A. This is called interior point. So what does it mean, an interior point? It means it's really inside. Okay, so not just point is inside, all the nearby points are also inside. So this is called interior point. You see, if you point on the boundary, even though the boundary is a point, like think about point on the solid line. So this point is in A, but it doesn't necessarily mean that nearby point will also in A. Some of the point very close to a point which is lying outside, not in A, right? So defining a point is interior point, requiring not just this point itself inside, but also the nearby point are also inside. Okay, so in the official definition, you are saying that a whole ball, a small ball will be inside A. So if a point carries this property, we can call this point an interior point. Okay, so but one thing I have to say that if suppose you are given a set, the set may involve lots of interior points. For instance, suppose a set is an open set. Okay, suppose you are dealing with an open, so every point inside the open set is going to be an interior point. Okay, because every point inside the open set, there's a whole ball inside the whole set. So every point inside, every point of an open set has to be an interior point. But it's also possible that you have a set, and this set carries no interior point. I think about a line in this. Think about you drawing a curve in the plane. So you think about a curve in the R2, the two-dimensional space, and this curve carries many points. But none of these points will be interior, because no matter how you draw a small ball surrounding this point, this ball must touch the outside of the curve. Okay. So this is called interior point. Now, a similar point is considered as the exterior point. Exterior point, this means that the point is completely outside. Okay, completely outside. This means that not only the point is outside, but also nearby point are also outside. So this means that there is a ball, BR, completely outside of A. So that's the situation. Okay, you can see that the point is outside, and also the whole ball surrounding X will also be outside. So that's called the exterior points. So you can, for a set, you can always define the interior point and exterior point. But there's the third kind of point. The third kind of point is not inside, not outside. Then that kind of point has to be on the boundary, right? So it's somehow stuck. Okay. A point is called a boundary point of A. Okay. The third kind of point is called boundary point. Now, boundary point is like a drawing point on the boundary. Now, what can you say about this point? Now, how do you define the boundary point? The boundary point is always more complicated than the interior point, exterior point. Okay. Because interior point, exterior point, you can use small ball to define. The boundary point, if you define using small ball, the statement will be more complicated. Now, think about a ball. Okay, think about a ball surrounding this boundary point. Now, what can you say this point? So no matter how small the radius is, this ball, because the point is on the boundary, so this ball must contain some point inside, or maybe not, but it must also contain some point outside. Okay, so the ball must carry the point itself, right? The point can be inside or outside, but it's also must carry a point outside. So the definition for a boundary point is like this. For any r greater than 0, the BR intersection with A equals to non-empty, okay? And the BR intersection with the complement of A is also non-empty. So that's why you can see, to define the boundary point, you have to pick arbitrary R, okay? I mean, for arbitrary R, both conditions hold. So this point is called a boundary point. Okay, so that's a definition for boundary point. So that's why you can see boundary point is more complicated. Okay, so both conditions are important. I mean, the BR intersect with A non-empty. So this means that the BR must contain some point inside A. If this condition is not true, suppose BR intersect with A is empty, so then you can see this X has to be exterior point. Okay, but it's not exterior, it's a boundary point. The second condition is also important. This means that the ball intersect with the complement is not empty. If the second condition removed, it's not true, so this means that the point has to be an interior point. So you have to have both conditions to characterize a point as boundary point. Okay, so that's the definition. Okay. So then we're going to give a name. So suppose you have a set A. So maybe the set A has no interior point. Maybe the set carries some interior point. So let's put all the interior point together. All the interior point of A together. So this is a subset of A, right? So this is called interior of A. It's called interior of A. It's denoted by A0. It's called the interior of A. Okay. Like here, the picture interior. And then, so obviously that the A interior is containing A is a subset of A because it's contained just interior, all the interior point. And the set A itself may carry some non-interior point, like boundary point, which is not inside the interior. Then you can also define exterior of A. That's the collection of all the exterior points. Okay, so they call it exterior point. But unfortunately, we do not have a notation for exterior point like A something. So we just can call this exterior of A. So the fact is that the exterior of A intersect with A is empty set. Exterior. Because exterior points means that, so these are points not completely, I mean, completely outside of A, okay? Not only the point itself is outside, but also nearby point is also outside. So obviously they have no intersection with A at all. Then we can call the set of all the boundary point of A, okay? All the boundary point of A together is called a boundary of A, okay? Unfortunately, we don't have a notation for the boundary of A, okay? But it's just there's a definition for that. The boundary point is like that. So given a set A, you can see based on these three different kind of point. So actually, it's divided the entire space into three different parts. The first part is the interior. The other part is exterior. The third part is the boundary. Okay, and because the union of all these three parts together give you the whole space. It's going to give you the whole space. Okay. Yeah, that's a very good question. And it's the set of all the exterior points. I mean, we talk about exterior of A. It's different from the complement of A. Of course, it's different. Okay. For instance, suppose A carries the boundary point, okay, the boundary point, and carries some portion, for instance, a part of the boundary is in A, a part of boundary is not in A. In this case, you can think about the complement. The complement must contain some point in the boundary. But however, exterior does not contain any boundary point. Okay, so that's why. You think about, or you can think about open set. And what is the exterior of open set? It's just exterior point without the boundary. Okay, the complement, that's the outside with the boundary. So that's a different. Okay, all right. So very good. Okay, so you can see this concept is very important. Okay, exterior, interior, and the boundary. Okay, and the next thing we want to, so we are going to continue to define something. Okay, we're going to call the union of interior of A and the boundary of A to be the closure of A, the closure. So what is closure? You take the interior and take the boundary point together. Okay, and so this is called closure, and it's denoted by A bar, something like this. And sometimes we put bar above A, sometimes on the right side of A. Different book carries different notations. Okay, so this is a very simple example. I mean, the situation, you take interior and the boundary together, you can see, so this is a new set, is called a closure. Okay, all right, so these are, so I'm going to, so this is the three kind of sets associated with A, okay? Interior, exterior, boundary, and closure. Now I'm going to demonstrate an example. Now let's say that you have set like this, it's a rectangular set, and you can see some portion of the boundary is inside, is with A, and some portion of the boundary is not with A. Okay, now with a set like that, what interior is, I mean, you remove every boundary point, remove all the boundary points, so remaining part is the interior. And exterior is being that outside, okay, so the point in which inside, which is not in the exterior, including the boundary or not. What is boundary? Boundary is just you close all the points on the boundary, so you get a solid boundary. Okay, now some of the boundary is in A, some of the boundary is not in A. Now what is closure? Closure means the boundary plus the interior. That's called a closure. Okay, so this gives you some idea about this this concept. Okay. Now here it comes to a theorem. It's a very important theorem we want to prove today. Okay, so that's the theorem is about the this kind of special set. You see, when we are given A, the A can be very complicated, very complicated. However, from A, I can define the interior, exterior, boundary, and the closure, 4 different kind of set. And these 4 sets are relatively simple. The A cell can be huge, complicated. There's a complexity inside the structure of A, but however, the interior, exterior, so this set is simple. Okay, now here's the result. So let A to be any set in RP. And then the first result is, I mean, this is something we don't need to prove it at all. I mean, it says that the interior belongs to A, and A belongs to the closure of A. This is obvious by the definition, right? Because the A carries some boundary point, carries some point are not in A, but however, the closure includes all the boundary points, so that's why the entire A is contained in A. Now, the key thing we want to prove is that both interior and exterior of A are open. Now, this is a very important result. A is complicated, but however, the interior and exterior, they are very simple. They are just open set. And also, the boundary point is closed. And also, the closure of A are also closed. So you can see that with a very complete A is given, and I can define these 4 sets. There are 2 of them are open, 2 of them are closed, are relatively much simpler than A itself. Okay, so that's the thing we want to establish today. The proof is not difficult. Okay, now obviously the first part is simple, so I just already say that things already, so I don't have to worry about that. Okay, so let's go to the B. The B part is crucial. So you can see the picture, and I demonstrate the interior of A, okay, by removing all the boundary point. And we also need to show that exterior are also open. But however, you can see that the both proofs are similar. So I only want to show that the interior of A is open. The same argument works to show the exterior is open, okay? Now, so what we need to show? We need to show that for every point in the interior, there is a ball also inside the interior in order to conclude that the interior is really open set, okay? So I began to pick an arbitrary point in A0. That's mean by a point in the interior. Now, what I mean by a point in the interior? So this a point itself is an interior point. So therefore, there is a small r, so that the BRX is inside. So here's a typo. It should be inside A, not belongs to A, inside A. Okay. So here's a picture. You can see that I have a point in the interior, so which is interior point. So ball. So by definition, the whole ball is inside A. Now here's a key step here. When I say there is a ball inside A, I didn't say that the whole ball is inside the interior. You see, interior and A can be different. Okay, so at this stage, we're just showing that there is a ball of X contained in A. And what we really want to show is that there is a ball such that the whole ball is inside the interior. We haven't reached to that yet. We only see that this ball is inside A. Now, how do you go from here to show that this ball is in the interior? What we need to show that every other point in this ball should also be an interior point, right? To conclude that. Now, there's a very simple way to handle this, because what we need to show that every point in the BR inside this ball is also in A interior, okay? And then you can see from here, you can conclude that the BR is in the interior. So X is the interior point of A interior. So therefore, A interior is open. Now, this is a key statement, okay? Now you need to think about this statement for a while. Well, after the class, you need to review this section and really try to make sure that you really understand this. Now here in the sequel, what we want to show is that I'm going to show that the ball itself is in the interior, not only in A. Okay. Now how do I show this? So I began to show that every point in this ball is an interior point. And it's very simple. So let's say you have Y. Y is a point inside this ball. Okay. Now you're choosing R1 small enough. R1 small enough, so that you can see the ball of the point Y with radius R1 will contain in the ball of X with radius R. So this will show that the interior, so Y is the interior point. It's an interior point of A naught. Now you can see a picture like this. So you can see the small point, okay, is inside the ball, and you can use a circle small enough. So the circle will be inside the big circle, right? So this shows that the second point here, Y point, is an interior point of this big ball. Okay, so this shows that the ball itself, BRX, is really inside the interior, not only inside the A itself. Okay, so this completes the proof. And same argument for the exterior point. Okay, using the same argument, you can prove the exterior. Any questions? Okay, so now let's move to part C. Now part C, we are going to show that the boundary and the closure are both closed. So I'm going to focusing on to show the boundary is closed. Now this is very simple, okay? Because we have already established that the interior and exterior, they are both open. So it's easy to see that the boundary is closed. Why? Because the boundary is equals to what? Equals to the whole space minus the union of interior and exterior. Okay? Now both exterior and the interior, they are both open. So the union is also open. So therefore the boundary is the complement of an open set. Of course. Of course, it shows that the boundary is closed. So the proof of part C is built on the part B. Okay, it's very easy because the boundary is the complement of interior union exterior. That's it. Now, how about closure? Closure is also easy. The closure equals to the whole space, the complement of exterior. Okay, because the closure is basically the interior plus the boundary. Okay, so it can be considered the complement of exterior. But exterior, we know that it's open, so therefore the closure is open. So you see both boundary and the closure, they're closed set. That's it. So that's the result. I mean, that's a proof of this important result. Okay, so today I would like to assign you the first two homework. Okay, so the first homework is that now the situation is slightly different. Now you can see here G is an open set, and you have a subset F in G, which is closed. Okay, and you prove directly that what do you mean by prove directly? So this means you prove using definition that the G minus F is open set. Now, if you draw a picture, you can see this obvious, but you need to write down proof. Actually, there's two ways to prove this. One is use definition, so that's a sign. So this is a required in this problem. So you need to use definition to show that this is correct. There's another global way to handle it. It's just using the previous theorem to do that. So I'm not going to give you any hint. I want you to think about it, and next time we'll come back, I'm going to talk about this. And the problem number 2 is similar. So now is you have a closed set is a bigger set. G is open, which is inside, and then you have to prove that the difference F minus G itself is a closed set. Okay, and again, this can be handled by definition, and also can be handled by the global property in the previous theorem. I'll show you next time. Okay, so we have introduced the closed set, open set, and classification of the interior and the exterior. So that's the important thing. But we still have on Thursday we have other thing. We are going back to the nested cell theorem. Okay, and the BW theorem in the high dimensional case, we are going to do that. Okay, and any other questions? So that is for today, okay? If you have questions, then we can talk about this in the office hour, okay? Okay, thank you very much.
Thank you.
Thank you.